Hi guys, welcome to another video on esoteric tech. Thank you guys for tuning in. It has been a while since my last tutorial video, but I promise I didn't forget about you, and we're going to keep this data structures and algorithms series rolling with this video on binary heaps, or what some will often refer to as priority queues. By the end of this video, you'll know exactly what a binary heap is. We'll talk about the difference between a min heap and a max heap. We'll know how and why to use them, and then we'll hop over to the code and I'll show you how to create them in Go. And as always, if you find this video to be helpful or informative, please do subscribe. Those subscriptions are the feedback I need to know if this content is helping and is actually informative. So thank you in advance, and let's go ahead and get started. A binary heap is a data structure that takes the form of a binary tree, and we've covered the concept of a tree data structure in our earlier video when discussing tries. And similar to other data tree structures, each node has a maximum of 2 child nodes, but in addition, a binary heap must have a couple other properties. It must follow the properties or conditions of a complete tree, meaning that nodes are added from top to bottom and left to right in order to generate a complete tree. And so this means that starting with the top, all levels are filled except possibly the last level. And second, a binary heap must be either a min or max heap. A min heap is a tree in which each parent node has a smaller value than its child nodes. And a max heap is just the opposite. Each parent node has a larger value than each of its child nodes. So your next question might be, what are they good for? Well, a binary heap is a good data structure for implementing a priority queue. And this is a slightly different queue from the one we've talked about in our previous video. In our previous video, we talked about the concept of a first in, first out queue, where each element is removed in the same order that it entered the queue. And this works pretty much just like a standard line that you would wait in real life. With a priority queue, elements are removed in the order of their priority. So when you insert an element, you sort them in such a way so that it is easy and quick to remove the element with the highest priority. Now you might be wondering, if we're discussing a binary tree, how is this going to be represented as a priority queue, right? Well, because it is a complete tree and all of these elements are essentially next to each other, that means we can represent this tree as a kind of list of contiguous indices. They're all right next to each other. And if we actually label the position of each one of these nodes, you can then see how they can be represented in the same type of list or array that you are typically used to when programming. And so conceptually, we think of it as a tree, but in memory, it's really represented as an array. And the side effect of this relationship between a complete tree and an array is that we have these very simple equations that we can use to find the position of a node's children or the position of a node's parent. So to the left here, what we have is the equations, or are the equations to figure out the left and right child. So for example, if I'm looking at the node in position 3 and I want to figure out where its left child is in the queue, well, I multiply it by 2, which gives me 6, and add 1, and its left child is at position 7 in the queue. And then with the right child, I just add 2 instead. And that is true for every node within this tree. And then on the flip side, if I want to find the position of a node's parent, I subtract 1 from its position and then divide it by 2. So hopefully I've established now that binary heaps allow you to easily identify the element with the highest priority. And that's because it's always going to be at the beginning. It's going to be at index 0. As long as you've sorted it the correct way. But the sorting is where the bulk of the logic and the coding comes into play here. So for example, if I wanted to add an element to this binary heap here, if I wanted to insert an element, well, I've got it inserted at the end, right? Because it's a complete tree, I have to follow the order. So I've got it inserted at, what is it, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, at the 9th index. So I insert, let's say 13 here, but this is not the correct position, right? Because we're in a min heap, it's got to follow the properties of that. So with a min heap, each parent node has a smaller value than its children nodes. And in this case, this is not true. So what we do is actually bubble it up. We compare it with the value of its parent node. And if it is smaller, then they switch positions. So 13 switches positions with its parent node. And then we do the same thing. We compare it again with its parent node. And if it's not larger, then it needs to be switched with its parent, right? And so we keep doing that until it gets into the position that it's supposed to be in. And so this is for a min heap. With the max heap, it's just slightly different logic, right? The parent is supposed to be larger than its child. So it's just a difference in the comparison operators that you're using. But that is how we would actually insert and then resort the binary heap. And then there's also some logic that has to occur when we remove an element. So if we actually remove that element from the front, that one with the highest priority, well, in that case, then it's a vacancy there. There's no element at index 0. And so what we do is we have to kind of resort. So we take the last element in the tree, or the last element in the array, and we put that at the very first position. And then we resort it. This is also known as heapifying. And so what we do is, and this is in the case of a min heap, what we do is compare it with its child nodes, and we switch it with the one that has the smallest value of the two, right? So we would put 41 on top, and then we look at these two children. Yep, the left child is the one that's the smallest between the left and right. So we're going to switch that one with the parent. And then we do it again. We're going to compare it with its left and right child. And in this case, its right child is the one that has the smallest value. And then we switch. And then we keep doing that until we get to the position where it actually follows the properties of a min heap. So the coding behind a binary heap is not complex at all. It's really using those simple equations that I showed you earlier to identify the position of a node's children or the position of a node's parent, and performing comparison operations to determine if they need to be switched around. And that's really all there is to it. And so we'll go ahead and hop over to the code, and I'll show you how to do this. So here we are in the code, and the first thing that I'm going to do is actually define a new type that will actually hold our queue in it. So this is going to be a type of min heap, and it's going to have a field called array that holds a slice of integers. And I'm keeping it simple with this. A lot of times when you look up the implementation for a binary heap, you'll have another type that's defined as the node that actually holds the data and actually the priority value. And then you've got an array of nodes, but then you have to access the value by saying node dot priority or whatever it is. And so just to keep it simple, I'm just going to have an array of integers, and the integer value is actually going to be the priority. So a few things that we know that we need. I mentioned that in order to do comparison operations, we know we're going to need to be able to find the index of a node's parent, and we need to be able to find the index of a node's children, or the indices of a node's children. And so we can go ahead and write those functions because we're going to be using those often. And we said that in order to find the position of a node's parent, that equation is just the index of that node minus 1 divided by 2. And then we're going to do the same thing for the left and right child nodes. So we have those functions defined, and also we need a function that will swap the position of two nodes. So this is going to be actually going to be a function of the heap itself, or a method of the heap. So this is going to be a pointer to a min heap, and this swap is going to take in two nodes, right? So it's going to take in two indices, and what it's going to do is swap around those values. Now we can actually go ahead and hop into the logic. The next method we'll go ahead and write is going to be our insert function. And this is going to be the function that allows us to take a new item and insert it into the priority queue. And if you remember what I said earlier, when you insert a new item, the first thing you do is append it to the end of the queue. So let's go ahead and write that. Okay, so I have now written the beginning of this insert function where we are appending the node to the end of the queue. And then I've made this call to this HeapifyUp method that I have defined here, but I haven't implemented yet. And so this HeapifyUp method takes in the position of the node that we just inserted into the queue. And then we're going to keep on heapifying it, moving it up the queue or the tree until it is in its correct position. And I'm going to switch over to this program that I put together in Unity just to make sure you guys are following me. So here we have a representation of a binary heap. And let's say that this here, number 17, is the node that we just inserted and appended to the end of the list. It's in the 11th position. According to the properties of a min binary heap, a node must have a smaller value than its child nodes. So we've already written the function to find its parent, and we can compare it. So we can see right off the bat, 17 is less than 62. That's not correct. And so what we would do is we would swap those nodes. And we've written the function to swap it as well. Now it's in the 5th position. And so again, we're going to do the same thing. We're going to compare it to its parent node. But the one thing you have to remember to do is you need to change the index that we are examining, because before this was in the 11th position and its parent was in the 5th position. Well, now this is in the 5th position and its parent is in the 2nd position. So we need to say, okay, we want to compare the node at the 5th position, which is the 4th index. I realize I'm saying positions. Maybe I should be saying indices, but obviously it's a zero-based list. So we're comparing the node at the 4th index with the node at the 1st index, and it was originally at the 10th index. And again, we can see this is not correct. That's the parent is supposed to be less than the child, and we're going to go ahead and switch those. And then we do it again, but this one actually is fine because its parent is smaller. And so switching back over to the code, if you're going to ask yourself, well, how many times do you need to go through that loop? Where you're going to keep going through it until it's in a position where its value is larger than its parent. And that's actually the first thing we'll do when we start off this function. While its parent is greater than the value of the node that we inserted, that's the index that we just passed in, we're going to swap it. And then, as I said, we need to update that index. And that is all you need to do for insertion. You append it, and then you heapify it, which is essentially a loop that keeps on heapifying it, moving it up in the tree until it gets to the correct position based on whether it's a min or max heap. The next method we'll go ahead and write is going to be the function to remove an item. And remember, when we are removing an item from the priority queue, we're always focused on removing the first one because that's the one with the highest priority. That's the entire point of the queue. And it's worth mentioning that you should remember that a priority queue doesn't guarantee that every single node in it is sorted according to priority. It just guarantees that the very first one in the queue is the highest priority. So I'll go ahead and write the code for this. And what we said is that when you want to remove an item, you pop the first one off of the queue, and then you take the very last one that's in the queue and move it to the very first position, and then you heapify down. So we kind of do the opposite of what we just did with the HeapifyUp. So let me go ahead and write this remove function. Okay, so in our remove function, the first thing we do is store the node that we're going to be removing and returning from this function. And then, and this is actually supposed to be outside of these parentheses here. So the next thing that we do is we're going to get the position of the last node in the list because we're going to move it to the front. And we actually do some error checking right here to make sure that the node that we removed wasn't the only node in the list, because if it is, then there's nothing else to move to the front. But then we go ahead and move forward. And so we set that position that's in the last position, or I'm sorry, that node that's in the last position of the queue. And this is a L, not a 1 here. We're going to move that to the front. That's what that's doing here. And then we actually slice off that last position because the queue now has one less node in it, right? It's one less index in it. And so we slice that off and then we heapify down. For this example, if we want to pop off the number 8, well, let's just go ahead and do that. So I'm going to go ahead and get rid of that node, right? And then I'm going to move that 62. All right, so the next thing we need to do is heapify down. And as I said before, this is the opposite of heapifying up. It's just a little bit more work because you have 2 other nodes that you need to compare it to instead of just the child node. But in this case, we can see that 62, you pair that to 17 and 15. 15 is obviously the smaller of the 2 children. And so we are going to switch those 2 positions. All right. And again, we do the same thing. We're going to compare it to its left and right child, but neither of those are smaller than this node here, so we know it's in the correct position. So that's what this HeapifyDown function is going to do. And then after it's done inserting the node in its correct position, we're going to return the one that we removed. So I'll go ahead and write the logic for the HeapifyDown function. Okay, so here in our HeapifyDown function, first thing we do is accept 0 because that's the position of the first index. And then we go ahead and store this value, last index to check. And this just refers to the last position in the queue, and you'll see why we get that in a second. But we're comparing it to its left and right child, so we get those values. And for now, we're just going to create a variable so that we can store the actual value that we're going to compare it to. So here's where we're going to use this last index to check. The reason we have that is because once we get to the point where the last index to check is equal to its left child, well, we know that it doesn't have a right child, right? Because that's the last one. And so in that case, we're saying if the left child is the last index in the queue, well, we know we only need to compare it to the left child. So we go ahead and set that. But if we have a left and a right child, and the left is smaller than the right, then the left child is the one we want to compare. Otherwise, the right child is the one that we want to compare. Next thing we want to do is actually go ahead and perform the comparison. So we're saying if the index that we're looking at, or the value of that node at that index, is greater than the child that we are comparing it to, then we need to swap it. And then what we do after that is the same thing I said to remember in the other function in the HeapifyUp, was to make sure that you update the variables that are holding these temporary indices. So we update the node position that we're looking at, and we update the children that we're comparing them to. And we're going to keep doing that until this here is no longer true, until we get into a position where the node has a smaller value than its child, and then we break out of this for loop. And so this is probably one of the more challenging parts of the whole, I guess, Heapify or binary heap algorithm. But once you get this, it's pretty simple. And so what I'll do just before wrapping up is go ahead and insert some elements into this heap and just make sure that I can sort it and that everything works perfectly. Okay, so I've gone ahead and written in the code to test this, and I did find one typo that I made here. Up here, I believe it was here, and within our remove function, I had written a 1 here, and that is clearly supposed to be an L because we're taking everything up to, but not including the last item in the queue. So I just want to make sure you guys are clear on that. That is an L, not a 1. I probably should have chose a different variable name. But what I've done here is just create an instance of our heap. I insert a number of different values, print it out, and then that's what you see here. So we print out all of those that have been inserted, and of course each time we insert, it's making a call to our HeapifyUp function, and then we remove it, which makes a call to our HeapifyDown function, and then again I inserted the number 6, and so you can see we've got the complete heap here. We removed 8, so it's no longer there, and then we inserted 6, which was HeapifyUp back up to the top of the list. So hopefully all of this makes sense. If you guys have any questions, feel free to post them in the comments. As I said before, I'm going to continue to make sure that I create more videos with this data structures and algorithm series. But thanks for tuning in. Please do subscribe, and I'll see you guys in the next video. Bye.